Welcome to This Explainer. Today we're diving straight into something that honestly sounds a bit like science fiction, but it's a very real and incredibly powerful framework. It's called the Basin-Quotient state machine. Basically, we're going to demystify how you can take the messy, continuous flow of physical oscillators and extract a lightning-fast, discrete logic system straight out of them. And the reason we are so focused on this today is because of what it means for the future of hardware. We're talking about the ultimate holy grail for engineering: near-zero execution cost and infinite scalability. By the end of this, you'll see exactly how extracting these physical rules points directly to the future of ultra-fast application architecture.
Okay, here's our roadmap. We're going to take a journey from the continuous geometry of coupled oscillators all the way to ultra-fast L1 cache applications. We'll start with the machine itself, check out its instruction set, test its physical limits, measure the thermodynamics, and then finally look at those incredible future apps.
So, Part 1. The Basin-Quotient machine. Literally, a computer built from physics.
To really grasp this machine, we first need to look at our container. Imagine a simple ring of 16 nearest neighbor Kuramoto phase oscillators. Now, because of the specific way these physical oscillators are coupled, they naturally settle into these resting places that physicists call twisted states. We aren't designing traditional logic gates from the ground up here. Instead, we're looking at a continuous dynamical system that just naturally forms distinct attractors. To organize these states and actually use them for computing, we use a winding number. That's a topological invariant representing the total wrapped phase winding around the ring. Think of it like taking a rubber band and wrapping it around a cylinder. You can stretch that rubber band, you can pull it, you can even distort the cylinder a bit. Those are just small physical distortions. But no matter what you do, the actual number of times that rubber band physically wraps around the cylinder, that cannot change unless you snap it. And that is exactly why this topological invariant is a perfect, totally robust discrete machine state label. It completely survives noise in the physical fabric, giving us a highly reliable way to label the machine state with just a simple integer.
Moving right along to Part 2, Reading, Writing, and Erasing, the Undesigned Instruction Set.
When you look at this instruction set, something wild stands out. It's completely emergent. We aren't forcing the physical system to compute. We're just discovering the computational rules that are already baked into its geometry. And there is a strict, undeniable difference between how it handles scalar inputs versus phase ramp gradients. Reading the state is just measuring that topological winding number, which is practically free computationally. Erasing? Also incredibly easy. You just hit the system with a localized scalar bump. Scalar inputs can only knock winding out of the fabric. They act like a one-way funnel, degrading the state back towards zero. But writing to the system, actually adding a winding number, that takes precision. You can't just use a generic input. You have to inject a highly specific, gradient-shaped 2π phase ramp. When you do that, it writes exactly one quantum of winding. It is incredibly precise. And it's exactly this level of built-in physical precision that's going to drive the hardware applications of the future. The system just naturally knows the difference between destroying data and meticulously creating it.
All right, Part 3, Testing the Physics Through Rigorous Interrogation.
To prove this system can actually function as a computer, we have to ensure it obeys strict digital logic. Because if the machine remembers its continuous physical history, it's not a discrete state machine, right? It has to forget the physical messiness and act like pure logic. So researchers threw 3 brutal Markov batteries of tests at the system. Basically, these guarantee that the machine's next state depends purely on its current label and its input. It entirely erases the history of how it got there. The first battery tests root invariance. This asks, if I take 2 totally different physical paths to arrive at the same state, does the machine behave identically going forward? Passing this means the machine doesn't get confused by its own past. The second battery is clock pressure. This probes the system mid-transient to find the absolute minimum wait time between inputs. In simple terms, it's finding the exact speed limit for computing on this physical architecture. Finally, the third battery tests composition. This proves that if you physically chain 2 inputs together in the real world, it yields the exact same logical result as just looking up those 2 steps sequentially in a spreadsheet. Passing all 3 of these proves this isn't just a fun physics experiment. It's a highly programmable machine.
And look at this table, the torus lens test. This proves exactly how robust this fabric is. What you're seeing here is what happens when you introduce a defect, a lens, directly into the physical ring. Now, if this system were unstable, changing one part of the ring would cause a massive, chaotic butterfly effect, ruining the logic everywhere. But that is not what happens. The transition table only changed right next to the edit, at physical distances of 0 and 1. The entire rest of the machine's programming remained perfectly intact. It's exactly like a dead pixel on your computer monitor. A dead pixel doesn't blue screen your whole operating system, right? It stays fiercely localized. This test guarantees our physical fabric is locally programmable and entirely composable, meaning we can build larger logic systems without worrying about cascading failures.
Let's move to part 4, the thermodynamics of computation, or its energetic anatomy.
Because this continuous ring acts as a gradient flow with a true energy landscape, we can do something absolutely vital for future hardware. We can calculate the exact thermodynamic cost of pushing the machine across the saddle point into a new state. This isn't a rough estimate. It is solved to machine precision using Newton's method. Let's look at this number, 0.348. That represents the coupling efficiency when transitioning states. To get this exact figure, you take the natural energy barrier of the system, which is exactly 1.133, and you divide it by the 3.258 units of energy that are injected by a physical kick. So why does this matter so much? Well, in the realm of future computing applications, knowing the exact thermodynamic cost to the decimal point is basically the holy grail. It means we can design future hardware that runs at the absolute physical limit of efficiency without overheating and without wasting a single drop of excess power.
Furthermore, these energetics enforce a strict, beautiful graph structure that guarantees stability. The math proves that without that properly shaped phase ramp we discussed earlier, inputs just funnel the machine down to a zero-winding state. Think of it as a brilliant built-in security feature of the physics itself. If you throw random noise, interference, or just unshaped scalar inputs at the system, it doesn't crash, it doesn't start spitting out corrupted garbage data, it simply acts as a safe eraser, reliably funneling the machine back to a stable zero state. The physics naturally protects the logic from chaos.
Which brings us to the ultimate payoff. Part 5. Future apps and something called the discrete shadow.
This is where the paradigm completely shifts. We're escaping the immense computational cost of simulating these physical oscillators to actually build the applications of tomorrow. There is a massive tension here between the computationally heavy discovery phase and the practically free, infinitely scalable execution phase. To discover this instruction set in the first place, you need massive, 1,000-node parallel server fleets running incredibly heavy RK4 integrations just to map out the continuous ring buffers and find the phase diagram. Huge heavy lifting. But here is the magic. Once that behavior is measured, mapped, and validated by those Markov batteries, you don't need to simulate the continuous physics anymore. You can literally throw all that heavy math away. You extract the discrete logic into a tiny lookup table of just a few dozen bytes. A table so small it can run instantly out of a CPU's ultra-fast L1 cache.
Let's look closely at this quote right here. Pay the integration cost once during discovery, then execute the discrete shadow at L1 lookup speed forever. This realization splits the future of computing architecture into two totally distinct eras. Modern servers become an ultra-fast phase diagram furnace. They are your expensive discovery instrument. You pay the heavy integration toll exactly once to mine the logic out of the physics. But from then on, your software executes what researchers call the discrete shadow. It runs directly out of the CPU's cache. It is essentially instantaneous, infinitely scalable, and the execution engine becomes practically free.
We've taken a messy, continuous physical system and successfully extracted a pure, hyper-efficient logic machine from it, completely paving the way for insanely fast hardware applications. So here's a provocative thought to leave you with. If a flawless logic system like this is hiding inside a simple ring of oscillators, what other software architectures are already written into the fabric of physics, just waiting for us to find them and extract their discrete shadows? Thanks for exploring this explainer with me today.